So let's now take a look at the pointer semantic side. We just looked at the value semantic side of things, right? Now let's go and look at a sharing example. So the code's going to look pretty much the same up front. We're going to be, again, let's go and get our new stack space here. Let's clean this up. And we're going to go and draw our stack again. So here we are. We drew our stack, and we're going to call into that main function. There we are. The Go routine is operating here. This is for the main, and it's also creating its own input inside that box. There it is, value of 10. We display the value of and the address of, but something a little different on line 17. This time, we're not making a copy of the integer value, what's in the box. We're making a copy of the address. Where is that integer? And this is still a pass by value, by the way. I want to make it very clear. This is not a pass by reference. This is still a pass by value, where the value being passed across the program boundary is an address. So it's real data, and it's real data that has to be stored. And if you're going to store real data, concrete data, then we need that variable. And so if you look at the parameters now on line 25, you can see that this isn't asking for an int. It's now asking for a star int. And by placing that star operator in front of the named type for the variable declaration, what we're really now saying is, I don't want an integer value, I want the address of an integer value. We're going to be storing that 4 or 8 byte value now inside our new frame. And a pointer variable is not a named type, but it is going to be a literal type. So you get the pointer type for free just by using star. And it's not enough to just say star. You might think, well, Bill, the star operator is what's dictating that I want addresses over other than like integers. But it's not enough to just ask for the address, because the whole idea of asking for the address is because you want to read and write to memory. And you can't read and write to memory unless you know the memory's type. So anytime we're dealing with a pointer, it's not going to be enough to say star. It's going to have to be the address of some actual concrete data that we're going to want to read and write. So now if we look at this on our stack, what we're going to have is that when that Go routine moves from this frame to the new frame, the variable inc isn't going to be a copy of 10. It's going to be a copy of the address where that is. And now what we're going to be able to say is that we're going to have indirect access to memory in that frame above us. Remember something, that the Go routine only has direct memory access to the memory inside the frame that it is operating on. It can read and write to this memory when it's operating in here. It can read and write to that memory when it's operating in here. But what the pointer semantics are doing, it's allowing this Go routine, even though it's operating inside of this frame right here, to reach out and be able to read and or write to data outside of its sandbox. This is where that side effect comes in. Because if we come back and look on line 28, what you're seeing now is the use of that operator, again, that star operator, to perform the indirect read, right? This is now saying, again, ++, read, modify, write. But don't read, modify, write the pointer itself. Go wouldn't let you do that anyway. That would be an integrity issue. By using the star, we're saying, let's read, modify, write the integer that the pointer points to. We're now leaving the comfort of our sandbox, and we're modifying data outside of it. This is the scary zone. This is the potential side effect that we're talking about. Anytime we're going to modify data outside of the sandbox, the frame that we're operating in, we have the potential of that side effect. And that's what the pointers cause. Now, again, we need the efficiency of the pointer. Instead of operating on our own copy of the data, the efficiency of that pointer allowed us to modify this in place. And that can add a lot of value around minimizing code complexity. But the big cost of the side effect is important. And now when the Go routine moves from this frame over to back to this frame on the return, we run this program. What we're going to see is that that number changed now inside of that frame for main. It now ends to be 11, where before it stayed at 10. So one of the things that I want to be very clear here is that when we're dealing with our pointer semantics, okay, what we're saying now is that the Go routine has shared access to something, okay, outside of this frame. When we talk about those value semantics, we're saying that the Go routine has its own copy of the data. It becomes very important for us to understand the differences in these two semantics because they're buried deep into the language. I don't want you right now worrying about, well, when do I use value semantics, Bill, and when do I use pointer semantics? Don't think about this right now. We have so much more to learn in terms of our mechanics. But what I'd rather you do right now is focus on truly understanding the differences between value semantics and pointer semantics. And later on, I promise, we'll start defining guidelines on when to use one semantic over the other for our data. So for now, I want to recap where we're at. There are two data semantics that we're going to be using in our program. There is value semantics and there are pointer semantics. Value semantics means that every single function call, right, every Go routine as it transitions from one program boundary to the other, is going to operate on its own copy of the data. Every function is going to get its own copy of the data, and what that's going to do is minimize side effects around mutation because that mutation is isolated to that one frame and that one frame only, right? It's a beautiful thing to do. It's going to give us our highest levels of integrity. It's going to give us levels of performance as well around data locality. It's really what we want to do. And Go is going to be a value semantic first language. We're going to want to use our value semantics first unless it's not reasonable or practical to do so. And when it's not, we're going to switch over to our pointer semantics. Remember, our pointer semantics add that efficiency where the cost of value semantics was inefficiency. And that efficiency is going to help us reduce code complexity. And it can help reduce a lot of code complexity. And plus, there's only one copy of the data we're managing instead of multiple. But there is a huge cost, that side effect cost that we just showed here. That Go routine transitioned from this frame into that frame, and the data had been modified outside of it, right? That's that side effect that I'm really worried about here. So when we're dealing with pointer semantics, we're going to slow some things down as we look at code, make sure that these modifications that we're modifying and writing isn't causing those side effects. We're in our value semantic mode. We can take it a lot easier, right? And we got to just continue to learn these different semantics as we move forward.